So it will be about very basic question, which essentially is interdisciplinary. It's not related to physics or mathematics or engineering. It's kind of something. So we really don't know how much we don't know and what we still can say about something which we do not know. It's a very general setting, and it's starting to be turned quantitative sometime in 19th century, and now it's getting kind of explosive growth. And so what I want to really give is to really, as they say, it's a biblical expression, standing on one foot, namely that somebody asks some sage, can you tell all the Bible standing in one foot? So I'll try to tell you all the thermodynamics and statistical physics in some time of kind of 10 minutes. And then I'll go into information theory. And I hope to convince you that information theory is just another way to tell the same story about thermodynamics and statistical physics. And then elucidate some kind of more technical points, which could be maybe helpful already, not only philosophically, but specifically. I apologize, there is lone movers move at this time, but it takes about 3-4 minutes, it will go away. So what I now want to say is that the one way to treat system for which we don't know almost anything is thermodynamics. Thermodynamics is a phenomenological approach. Namely, we don't know what is a microscopic inside, but we know the nature of the system inside. In a sense, we assume that what is inside somehow satisfies some symmetries. And this symmetries means that there are some transformations that you can make with it and it will still be the same. And then we want to restrict behavior, impose some inequalities from these symmetries. So thermodynamics never computes things, it imposes inequalities on the behavior. And of course, the basic symmetry is that we assume very often is that tomorrow's system will be the same as today, namely that it statistically must be translational in time. Not all systems are like this. If you want to study, for example, yourself or any living being, then definitely tomorrow more or less the same, but in 10 years we are different, or in 40 years we are different. Or you study stock market, it could be very much different sometime from now, even statistically. So be careful, but generally we assume this thing. And that means that translational variance in time means some quantity is conserved and this quantity is energy. So energy is a conservation is a consequence of time translation invariance. And we assume that the systems that we study could be really isolated from all other systems, and we can visit every state of the system and measure energy in this state. And how we measure it? We just measure work done to bring system from state to state. And then we let system evolve, not isolated, and then we notice that the energy change, which is here on the left, and it's a differential. Differential means that there is some function, and for every state you have some energy. So when you go from state to state, it's always a differential of some function. But then we notice that it's not exactly equal to minus the work done on the system. This is delta V. Work is not a function of a state, it's a function of the process. So this is why it's not a differential. So, and then we say that, okay, if our energy change is not equal to the work done, then there is something hidden, and we call it heat. It's a very general framework. So we have explicit degrees of freedom, for example, volume. We measure volume, we measure pressure, we do work, we measure it. But there is something else changes, and this something else, which is related to hidden degrees of freedom, we call heat. And then, what kind of a basic problem of thermodynamics that we solve? We want to say, okay, now if we let system live as it is, what will be its finite state? And people in 19th century, mostly working with thermal engines and all this works and energy transformation, they found empirically the principle that there is some quantity which characterizes the system. It's called entropy, and it reaches maximum. It was really, I mean, I can talk hours about history of it and all the dead ends that people found, but let's say empirically they found it. It's a function of energy. And generally, entropy and energy are related by some kind of a convex relation, not necessarily monotonic, as we can see later, but it tells us that all the possible states are below this line. This line is a maximal possible state for every energy. So if you go at a given energy up, at some point you reach the equilibrium state, which is on this line. On the other hand, if you fix your entropy, then for by energy you can go down. So the equilibrium state A is a maximal of entropy at a given energy and a minimum of energy at a given entropy. That's more or less all the thermodynamics. Now see how it solves the problem. It tells you that you can define the derivative of energy with respect to entropy, and it's called temperature. You're a physicist, the moment for you temperature is not thermometer measures, but the derivative of energy with respect to entropy. And it could be negative. I mean, you're a physicist when you really can afford negative temperature, imaginary temperature, doesn't matter. It's a derivative of energy with respect to entropy. Then see how it works. We have a system which can, let's say, consists of two parts, 1 and 2. Its total energy is fixed. So we want to know when it will be in equilibrium. Well, we say we know it will be in equilibrium when entropy is maximum. So let's differentiate entropy. So it's a derivative of a first part and derivative of a second part. But this is 1 over temperature and this is 1 over temperature. So it has this form. But dE2, because of energy conservation, equal to minus dE1. So we get this. So we see that the entropy reaches its maximum when T1 equal to T2. And T here could be negative, for example, as it happened for two-level system in some state, for laser, for spins in a magnetic field. Good. Now statistical physics. It's a next level of sophistication. Now we know what are the microscopic degrees of freedom. But there are so many of them that we cannot really solve this. We want to somehow average over them. And now we want to use a specific knowledge of what is the type of degrees of freedom they have. And then we say that if we really want to characterize a system, so we need to relate our entropy, which was a thermodynamic quantity, to something microscopic, to something which characterizes the state of our system. And that Boltzmann discovered it, and this formula is written on his grave. If you'll be in Vienna, you can find it. It's a very prominent monument. Actually, in Vienna is the most interesting part of the cemetery. So it says that we can define gamma, and gamma is the phase volume. If you know what are the variables of your system, momenta, coordinate, you can compute the phase volume, how much it occupies in this phase volume, and the entropy is a logarithm of this phase volume. How it solves our main problem? Again, we have system 1 and 2. We say that in principle, the phase volume is a sum over all possible division of energy. We can give a piece of energy to the first system, 2 pieces of energy to the first system, 3 pieces of energy to the first system, and to the second system we give the rest. And now we ask what kind of partition in this case, what term in this sum corresponds to the maximum. Of course, we again compute the derivative of it with respect to the energy that we give. Again, we obtain now that gamma is an exponent in the power s. So we can express it in terms of the derivative of s entropy with respect to energy, or energy with respect to entropy, which is again T1 equal to T2. Okay? So essentially, this is how statistical physics solves this problem, and it identifies entropy with a microscopic state of matter. And then we can look at a system which is not isolated, but a part of a big thermostat, and we may ask what is the probability to find this value of energy of the system. That Gibbs did it, and he says it must be proportional to the how many states of a thermostat. Gamma is a weight of the thermostat, is a number of possible, the volume, phase volume of thermostat, at an energy which is energy of the thermostat minus our energy E. Because we assume our system is very small, then we can expand this E with respect to this E naught, and we obtain Gibbs distribution, because essentially, again, will be differentiated entropy with respect to energy. It would give us temperature, and all comes out of thermostat here is just this temperature. Okay, and now it tells us very interesting. The probability is exponential in energy. So entropy, which was a logarithm of a number of states, which is minus logarithm of probability, we can ask, is this entropy is a logarithm of probability taken at mean energy, or it's a mean value of probability, namely takes the logarithm of V of every energy and average it over energy? The answer is it's the same, because the logarithm of W is linear in E. So the mean value of E is equal to mean value of E. And that gives us what is called Gibbs entropy, which is the logarithm of W averaged with the W. So W is the probability of any given state, and this is the entropy of a system. And then we can find the Gibbs distribution, again requires the extremum of entropy with respect with the extra condition of a fixed mean energy. So that's more or less in 10 minutes the thermodynamic and statistical physics. I just want to, I'm sure you all know it, I just wanted to recall it and recall it in kind of very compact way. Now, it all looks wrong. The moment you start thinking about it, it's something which kind of beautiful. I mean, we all learned it. And 40 years ago at Novosibirsk University, I remember I was taught this, and then I was told that no, it's actually very paradoxical. And these paradoxes go back to Boltzmann, and some even say that it cost him his life. First of all, Boltzmann and other people ask how something which belongs to a system, and system is mechanical system, how it could evolve irreversibly if the system is time reversal. All mechanical system, all equation of motion are second order in time, they are all time reversible. On the other hand, if we have a Hamiltonian system, which is more or less any dynamical isolated system is Hamiltonian, then it just has a Liouville theorem, namely it preserves its phase space distribution, its density in space, and then it must be also preserving logarithm of it, which is entropy. So entropy could not be time dependent. And then Maxwell added to it, or actually did it even before, because it was before Boltzmann, with his Maxwell demon, he says that we can actually decrease entropy because we can really use some kind of knowledge, and we can open and close the door in the right time so that the hot molecules would be in one part, or blue molecules will be in one part and red molecules in the other part, and that would decrease entropy, because that would any separation decrease entropy. And one word resolves all the three paradoxes, and it was already known 40 years ago when we were tortured by this, and there's still many people all over the world tortured by these paradoxes. The answer was actually found again in this Novosibirsk University. Rumor told us that at 20s in Berlin, at 28 actually, they asked Einstein to lead a student seminar, and Einstein asked them, what you want the seminar to be about? And they say, well, probably about relativity, this is or quantum mechanics, they are the most sexy subjects. They say, no, we'll have a seminar about the timeless subject, which is statistical physics. And one of the young guys who attended the seminar, Leo Szilard, actually started the information theory. So let me tell you, what is information? So let's imagine that we want a candy. Candy is in a box, and we don't know in which box it is. So we want information about where it is. So we now want to measure this information, how much we got when we found the candy. So we can say, well, it may be dependent on how many candies is there. But apparently not, because it's not about how many, it's about where. And apparently, if there is one box, we don't need any information. So I of 1 must be 0. What if we have not n boxes, but nm boxes? What do you think? How much information we would need? Well, we can think that actually you have every box divided into m compartments. Then apparently you need information in which box, and then you need information about in which compartment inside this box. So apparently information must be additive when the number of states is multiplicative. And it's already clear from this that it must be a logarithm. And in particularly, we can measure information in bits. Leo Szilard, in his PhD, which was 8-page document that he did in 2 weeks, also introduced the word bit in Berlin in 1924. So we say that the amount of information would be logarithm by 2 of the number of boxes. We can ask the first question, it's a left half or right half, and then we'll be dividing by 2 the number of boxes until we come to a single box. Apparently, it could be all generalized for non-even or even non-integer number of n. It's just the function. But what if we are now talking about boxes which could be coming with different probability? For example, our boxes are letters of the alphabet, and those are from A to Z. And we get the word love, which are 4 letters, namely we made 4 choices out of it. But we know that the different letters in the alphabet, they come with different frequencies. Okay, so we have these WIs frequencies, which are now bring to mind the Gibbs distribution. So now, because it's something which comes with definite probability, we may ask what is the average information that we get when we obtain a symbol, or what is the average information when we obtain the 4-letter word, no matter how statistically or emotionally significant the word love would be. And this is Shannon probably, who, there was several people before them, but Shannon made a giant step. It was this way of looking into information statistically. It's kind of strange because it assumes that you get many messages, and essentially the meaning of any message already kind of blurs here. It happened to be very powerful in engineering way, but it was a very huge conceptual jump. It was really very difficult for people to start talking about information in some kind of an averaged way. So let's ask this question. When the number of symbols goes to infinity, how much information every symbol brings on average? So what do we know? We know double WIs. Those are probabilities of a symbol number I. W1 is the probability of A, WB is the probability of B. So we know that even when the sequence is very large, then each letter happens that many times, NWI. What we did not know, and what any given message brings, is a particular order in which different symbols appears. So the information which any message brings is a logarithm of that number of orders, because that's where choice happens. Number of orders in which letters actually appear. And it's now an easy combinatorial problem. You take the total number of messages, and then you divide it by the fact that you know that every message number I happens that many times. So now that would be your total number of orders. If you take a logarithm of it, and you use Stirling formula, assuming that n is very large, you get the following thing, that the information which the message of length n brings is proportional to n, and the coefficient of proportionality is a Gibbs entropy. So this is a formula, and in particularly now, if you go and compute it for English, you would get 4.11 bits, which is different from 4.7 bits if you would assume that your letters would appear unequally. And really, entropy of English, just to mention this, is even less. It's really 1.4. And this is 1.4 is that there is not only probabilities of different letters, but there are probabilities of different letter combinations. Some letters actually could be omitted, and every language is about 2/3 redundant. English is even 70 plus. Russian is a little bit less than 70. And this is the last line. I now want you to read it, each one of you, and try to see if you can read this line. It's a very famous poster from New York City subway, which was really used, and people really understood that this is an advertisement for a job, and people who really were able, mostly girls, to read this advertisement, they came and get a very good job. So if you can read this, you can get a good job with high pay. That was an advertisement for secretary work. It demonstrates the redundancy of English language. And of course, the meaning of this redundancy was understood sometime before this by Shannon and other people, that it was needed to protect your communications. So again, let me reiterate here. At some point, it appeared that just asking about information understood as a choice out of different possibilities brings a formula which was the same as the formula of thermodynamic entropy. At that point, it looked a little bit mysterious, and there is this famous saying of von Neumann, who advised Shannon. Shannon used it uncertainty initially, and von Neumann advised him to call it an entropy because nobody would really know what it is. As they were very actively interacting. I mean, von Neumann, Turing, Shannon, they were coders, decoders. There was kind of very active interaction. Now, what Shannon established is essentially a communication theory, because it was really interesting that how we transfer the data. It's really important to see how people in every century were solving different technical problems, and it caused the shift of orientation, but they were essentially doing the same. 19th century people were building engines. 20th century people were doing communications. Energy and matter is less and less important in 20th century, and even less so in 21st century. We pay less and less people who do things. We pay more and more people who just move bits around. So that Shannon asked how much we can compress our data, namely how fast we can transfer information, and can we really transfer it without errors if there is noise, which essentially means unknown factors. And that's how this idea that on average, if you take symbols out of some alphabet and symbols or objects come with the probabilities, that the mean rate of transfer is W logarithm W, which is Gibbs entropy, and what Shannon proved that it's actually the maximal rate of transfer. Okay, so is it really you cannot transfer faster on average. You can transfer slower, and unfortunately, most of Shannon's proofs were non-constructive, but still was very important. And so this formula, the Gibbs entropy, gives the minimum number of symbols which you need to transfer the ensemble of messages. This is a very engineering approach, because philosophy was still arguing about meanings, and it's very interesting, but it's not very practical. And at some point, somebody started to use information without any relation to meaning, and it used to and happened to be very, very powerful. Okay, now of course you can change this rate by just coding. So you may look at some letters which happen very often, and then you can code them by very short sequences. That's what Morse did, by the way. Morse was a painter who was painting Lafayette, and then he got a message that his wife died. And this was on South, and so he needed to get back to Boston, and he get a message that the wife is ill, but the time he got there, wife already died. And after that, he never painted anything. He devoted the rest of his life to devising a way of fast communication. And that's actually what he did. This idea that you really code things and you code it in an effective way. And you can do in this way some very lossless compressions, like things that we all know, like zip, gz, and other. Okay, so now we want to a little bit turn it around and say, okay, but we usually, if we know the distribution, if we know this WI, then we know how to get information rate and all this. But let's say that we just measure something about our system or get messages about our system, but we don't know information. We don't know distribution. So we have some quantities R, which depends on whatever variables, but only mean values of this. Namely, we measure it many times, get mean value. So how to get the distribution? And the idea is that to get a distribution, it must be true, namely corresponding to all this information that we get, but it can contain nothing but the truth. Namely, it means that it must maximize all the missing information that we did not give. But the missing information is exactly entropy. That how much we miss about the system, it's an entropy. So really, if you really look at the variation of your entropy under the conditions that you measured things, you would obtain the kind of a generalized Gibbs distribution, which is a very powerful, which tells you that there is nothing specifically equilibrium about Gibbs distribution. It's actually just an extremum of entropy under a given condition. So there could be different condition, and the system could be whatever you are, whatever you have. You just say that your distribution contains the whole truth and nothing but the truth. That's essentially the statement that you look for conditional extremum of entropy. And this is now more or less looking for this extremum and how most artificial intelligence systems really work. They are always looking for some kind of extremum under condition, and they tweak the parameters and coefficient in this, coming closer and closer and closer to this extremum. And there are very, very technical and very involved things, but conceptually this is essentially what they do. And then looking at this as an entropy, which is a missing information about the system, immediately resolve all the paradoxes. Because it tells us that entropy is not a property of a system. Entropy is a property of our knowledge or better ignorance about system. It's unbelievable how much time it took, my estimate 60, 70 years, since this statement was understood until it percolated into textbook and university courses. I was teaching this course here at the Weizmann Institute, and some very prominent scientists, better than me, really great scientists in brain research, after my lecture came, here we have also professors coming to lectures. It's a nice place. You say, Grisha, what you are saying is that the law of statistical physics is not like laws of mechanics. It's not about the world, it's about us and the world. And I said, yes, of course, but it could be that also laws of quantum mechanics is also not only about the world, it's about the way that we understand and perceive the world. And this is essentially what Szilard realized, that first of all, the understanding that if we have information about the system and it grows, entropy grows with time, it grows also into the past. So in a sense, if you want to predict what happened in the past, your information at a given time is less and less relevant as you go back into the past. Information ages. It's getting less and less relevant to your system because you know a system with a finite precision. Okay, so from the viewpoint of information, all the statistical physics statement, which looks so objective, about approaching equilibrium, is just equivalent to say that we forgot all the information except integrals of motion. Equilibrium is totally determined by its integrals of motion, and it corresponds to a maximum of entropy, means that whole information is forgotten. And then another thing, which is important, and which Szilard did, is that he told us, and then it was, of course, understood in my, and there is a lot of work still going on. He told us what is actually the price of information. Because as Maxwell noticed that if we know in which part of a system is a molecule, then we can get work out of it. And indeed, Szilard says that you can build an engine. So if you know where is that your molecule is in the right-hand side, so you can put your membrane in the middle, but not only you put a membrane in the middle, you attach your weight at the right, because you know that the molecule is in the right and it would push your membrane to the left. So this knowledge allows you to get a work, namely that when the membrane would be going, then you can do, you can raise your weight. And it essentially tells you that depending on which temperature you are, you can get work which is energetic price of this information, which is kT logarithm 2. And it means that if you really believe in the conservation of energy, that to get this information, you need to spend at least that amount of work at some time before to get it. And of course, I would probably want now concentrate of it, but the next step in this way was done by Landauer, who says that if we really think about the system as a cyclical process, namely we want to kind of do it over and over and over many cycles, right? Because that way we would try to build a perpetual mobile of a second type. Namely, we will be turning thermal energy of my molecule. We keep system all the time at a temperature T, it's important. So essentially we take energy out of environment by using this information. And then what Landauer have shown us, that there is one very important step in this process, is that you need to erase this information if you really want a cyclical process. Otherwise you would need a storage for this information. And for this, when you really will be doing this erasure, you would be releasing heat, which is again no less than your work. So that's how we really exercised the Maxwell demon. Somebody said that Sillard exercised the Maxwell demon, but it still haunts our castles as a lovable poltergeist. So it's only at 70s the experimental work on this Sillard Landauer engine was done. It's a beautiful paper in Nature, I guess 73 or 74. Okay, so that's how we connected our information with, and then what really appeared as a next step, and it's really a magic wand which now used all over the physics and engineering. It's an idea of unusual information. So now let me introduce this idea, because this would be probably the most important practical part. So when we get a message, or we measured something, we get an information, is it true or something was lost in the way? So how much actually we learned about B if we got A? And so somehow it must be related to the fact that if we observed A, it somehow increased the probability to have B. Event B could be that some quantity has a given value. So we can define this thing, which defines the following. It's called I from information, and it's a logarithm of a conditional probability of having B in case A happened, divided by unconditional probability. Apparently, what stands here is larger or equal than what stands there, so this quantity is always positive, and when this equal to that, namely A brings nothing, then it's 0. We can also express, of course, the conditional probability through a joint probability. We can say that, of course, the joint probability of having B and A simultaneously means that we have a probability of A, and then we have a probability of B in the presence of A. So we can now substitute here this expression and get a very symmetric form, which tells us that the mutual information between A and B is the same as the mutual information between B and A. And it could now be averaged over all possible A's and B's. And it's a simple exercise which everyone could do. It's still exercise, it's like two-line computation, that you can show that this is an entropy of A distribution, whatever it is, could be 0, for example, if it's something which is non-random, plus entropy of B minus entropy of their joint distribution. So it is this diagram which my student, I mean, she is a mathematician, she hates it. It's just your physicist way of pretend that you understand something, but by making pictures. But I still like it very much. It actually tells you that this is S of A, and this is S of B. This is a big one. So if I make a joint of it, it would be S of AB. This is a conditional entropy of one, this is a conditional entropy of another, and the intersect is a mutual information. It's called Venn diagram, and I find it helpful, even though Mathematicians find it atrocious. So now, let's just look at this and a little bit meditate on this relation. So first of all, when A and B is independent, the conditional probability is, the information is 0. When they are dependent, then definitely the joint probability is larger than this, because they are dependent, so it's not a product. And the information is positive. Then when they are equal to each other, then again, it's their joint entropy, their mutual information, etc. And it is this relation, which is also very technically useful, and particularly its quantum analogs, which I don't know, it probably won't connect. So now Shannon used this idea of mutual information, understood as, and he used it to define a channel capacity. Namely, that he just averaged, maximize over all possible sources statistics, because let's say that you are interested not in the quantities that you measure, namely B's, but the measurement itself or communications. You are not interested in the sources. Sources B could have different statistics. So you say, what is the maximal over all the sources of this mutual information? And you call it the channel capacity. And the channel capacity is essentially how fast you can transfer the information. And it allowed Shannon to answer the second important question. Remember, there was 2 questions that he asked. The first question was, what is the maximal rate that you can transfer information? And the answer was, asymptotically, it's the mean rate, namely entropy. And the second question, can you transfer error-free even though you have a noise? Before Shannon, people believed that you cannot transfer through a channel with a noise error-free. Because no matter how long you transfer, your errors also add. Because you transfer longer, your errors accumulate. And Shannon shows that it's not the case. And the crucial thing here was this channel capacity, which is essentially the mutual information. Okay, so in a sense, this channel capacity, you can say that it's a maximal number of distinguishing signals. Let's see how it works. So if our channel transmits binary, namely zeros and ones, and if it transfers it exactly, then the capacity is 1 bit, which means that you just take P of B0 equal to P of B1 is 1/2. Now, if your channel has many output for every input out of n, the capacity is still just an entropy, it's just a logarithm of n. Because if your outputs are non-overlapping, they are distinguished, that's okay. But what really happens with what noise mixes is that when your outputs appear the same for different inputs, okay? So you have groups of m inputs and each gives the same output. So essentially, your conditional probability of having B under given A is 1/n, okay? So this is your probability. So now you can compute your mutual information, okay? Because the probability of B would be m/n, and then the chosen, sorry, I just jump it. How I can move it? Probably like this, okay? So you see that now your mutual information would be logarithm of n/m. So if m is not equal to unity, is larger than unity, you actually lower your rate of transfer. Your rate of transfer was entropy, which is logarithm n, how many possible values of B. But if there is m values of B for every received signal, then you lower it like this. And it means it just you, it means also increase redundancy, that you need to send more symbols to convey the same information. This is the kind of the most trivial combination, namely that we can really distinguish different inputs by combining them into groups, because for every A you have m different B's, like in this formula. Sorry, I just forgot to switch off my phone. Now, of course, you can do it in a more sophisticated way when you use in noise, but essentially it's the same idea that if you really have a noise, you really need to separate your input symbols into group, and capacity of mutual information essentially tells you this. And capacity sets the limit, because what Shannon proved is a theorem, and I'm definitely not going to prove you any theorems now, but it's really could be understood that if there is any connection between A and B, namely, if there is any connection, that mutual information is positive. If mutual information is positive, then its maximum over all possible statistics of sources is larger than 0. If it's larger than 0, then the probability of error can be estimated like this, where R is a rate with which you transfer information, and C is the capacity of a channel. You see, it's a very important statement because it has N inside. It tells you that when N goes to infinity, your probability of error is getting asymptotically small, as long as your rate of transfer lower than your capacity. Okay, this is really the way that you assume that you get error-free communication in the limit of N going to infinity. This is probably the most important result of the communication theory. It's still non-constructive in the sense that it does not tell you how to do it, but there are many constructive results in this way. And again, what is the most important quantity here is the mutual information. You see that the mutual information is really plays the role of entropy, because the moment that you have a total correlation, then information that you get is an entropy of your source distribution. The moment there is an incomplete correlation, instead of entropy, you need to use mutual information, which is this essentially degree of correlation. But now we can use it and return back to Boltzmann. I remember that was just the moment that I've realized it. I was mad at my teacher, why they tortured me by all these paradoxes. So this mutual information lets you to look at the second law of thermodynamics in a really trivial perspective. Because what essentially Boltzmann said, he said that if you take, the Boltzmann entropy is an additive quantity. It's defined in thermodynamics as an extensive quantity. If you look at the different, let's say, particles of a gas, it's just a sum of entropies, okay? So it is this quantity which is grows, say, so if you really say that you can take a true entropy of all your particles of whatever system characterized by momenta and coordinates, this is S, and take a Boltzmann entropy, that what their difference is a mutual information between different particles or different subsystem of a system. Now, what Liouville's theorem tells you is that the second term, S, the total entropy, is conserved under evolution. What Boltzmann tells you is that this quantity grows after evolution. How Boltzmann established it, he said, let's start from uncorrelated particles, and that you will see that their entropy grows. But because S is conserved, the growth of Boltzmann entropy, which is the first term, corresponds to the growth of mutual information, which is the last term. So you can say the second law of thermodynamics in the following form. The true entropy is conserved. It's a Liouville theorem. It's equivalent to the Boltzmann statement, because other way to say it is to say that as particles evolve, they're getting more and more correlated. So their degree of correlation grows, which means that the entropy, if we would assume them uncorrelated, would increase. But the true entropy, of course, does not change. And in a sense, this is a way, it's now one of the three ways in which we reformulate second law of thermodynamics. In 20th century, there is another way to reformulate it in 21st century, which I probably won't talk now, but it's again turning second law of thermodynamics into equality, not into an inequality. So again, let me reiterate it, because despite its triviality, it just shows you how actually uniform all our knowledge. So what we learn from information theory is essentially allows us to look at the statistical physics in a really trivial way. And so in a sense, so what Boltzmann say is that if we really want to consider entropy of uncorrelated particle, it means we just forget all the correlation knowledge which appear, but this is our choice. This is not something which happens in the system. It's us, our renunciation of all correlation knowledge. That's what actually leads to the entropy growth. Okay, and here's maybe a couple of remarks. What is the real redundancy that we see in the world? For example, and again, redundancy means that your capacity is larger than your transfer rate, so that your error rate goes to infinity. For example, we have a genetic code, and there are 16 two-letter words, and it's not enough for 20 amino acids. So we now use a triplet code, but triplet code has 64 words, so the redundancy is about 3, and indeed, we encode different amino acids more or less proportionally to the frequency in which they are. Now, the next interesting question, it's very non-trivial, which haunted science for some time, is what is the rates of transmission of genetic code and what would be error rates of such transmission? So what is really error would be if we have a DNA base pair mismatched, okay? And the price of it is just the probability that the hydrogen bond is broken, which is about 10 times the room temperature, the energy of it. So if we would take exponent minus 10, which is essentially 10 minus 4 per one base, we would all die. There would be never ever any life on the world because we have 300 amino acids per protein. They are encoded by this number of bases. So if you multiply 10 to 3 by 10 to minus 4, then 10% of our proteins would be faulty, and that would be totally deadly. Okay, which shows us that the fact that we all living beings live is that, of course, all our probabilities are not Gibbs probabilities. The probability of mismatched pair is not exponent minus energy divided by temperature. It's much, much, much less. And this follows from the fact that we are highly non-equilibrium state, which uses which uses a lot of information. And this information, it's because any extra information means deviation from equilibrium. And this is also, maybe I'll make a remark of a general nature. I found it some kind of inspiring, that if somebody would ask 100 years ago what you need for a life, then people would normally answer energy. And it's nonsense, because any living being does not consume energy. We emit as much energy as we absorb. Energy is a conserved quantity, right? So we eat chocolates or fruits, and then we emit body heat, and it's about exactly the same amount of energy. What we really consume, we consume information. So what we eat, for example, is highly low entropic sources. If you imagine how much information people process to pack 400 calories into 100 grams of chocolate, it's a lot. And what we emit is a body heat, which is a very, very high entropic source. So what every living being does, he lives in a very non-equilibrium state. He uses energy flux through it, not consuming energy, just interrupting this flux from a very low entropic source to a very high entropic sink. And plants do the same, by the way. Plants get energy from the sun, and then they emit heat. But sun is a very, very low entropic source because it has very, very high temperature. If it's a very high temperature, then for the same amount of energy, it loses a very tiny bit of entropy. Okay, so this is really important to understand that information, any extra information, means deviation from equilibrium, and that essentially what life uses. As Dawkins says, that if you look at every living being, what is there is not a spark of life, it's just an information in bits. And so now let me more or less conclude and reiterate what I was saying. So first of all, I reminded you about statistical physics and kind of briefly presented it, and I believe I've shown it that in a way statistical physics is a way of saying something about systems that we don't know. We're doing it every century, just using different objects, because we were interested in how to do engines. Now we're interested in how to compute or how to communicate. But essentially, the question is always the same. What are restrictions imposed on what we can do and what we cannot do? And then what we discovered is the same quantity appears over and over and over again. And it is a mean logarithm of a probability distribution. And we call it entropy. And then we understood that it's, on one hand, is a minimum descriptive complexity of random variables. And it's also the ultimate data compression rate, as shown by Shannon. And then we learn a next step, a next sophisticated thing, which is a mutual information. A mutual information is something which characterizes your procedure of measurement or your channel of communication, and it's a degree of correlation between source and sink. And looking at the maximum of it, we define channel capacity, and the channel capacity is the ultimate transmission rate of a noisy channel. It is this noisy channel which disrupts exact correlation between input and output and lowers the rate of communication, but not to zero. If any correlation between source and sink exists, you can always find a non-zero rate of communication, which has asymptotically zero error rate. So now what this mutual information is essentially a universal tool, and I teach the whole course about how it is used, from self-driving cars to entropy of black holes to it's very similar to what people use in entanglement entropy in quantum physics, and it's essentially a very universal way of finding mutual algorithms, either minimizing mutual information when you really want to divide, for example, your input into independent components. For example, when we have a visual input, when you look at me, you see a lot of things which are highly correlated. It's highly redundant. Most of the pixels in this picture, they are correlated with each other. You want to break it into few uncorrelated components, you minimize mutual information. You want to then, having this information increase its transfer rate, you maximize mutual information. So if you look at all the papers from people, again, who do image recognition, self-driving cars, artificial intelligence, they're mostly playing with this functional, either minimizing or maximizing us using different empirical or theoretical extra condition and looking for conditional. On the other hand, maybe last thing that I want to say is that it's really now led us to look at physics in a different way. I think that the main reason why we were all tortured by all these paradoxes when already, you know, after Shannon, Brillouin, and Szilard, is that it was very difficult for people to appreciate that something is non-objective in our science. You know, they wanted to keep scientists out of science. It looks like very decent thing, like, because science must be objective. It should not be dependent on who are scientists, right? But already when you read Maxwell, Maxwell understood probably most of it. Maxwell say, if you are a God Almighty, you don't need statistical physics, right? So statistical physics is something which is made by humans for humans. And then, of course, what people really now tortured and look inside, is it quantum mechanics also this thing? To what extent is this, is it not only about physical nature of information, but informational nature of physics? It is very many people who are really now trying to look into this direction. So I believe that all this kind of change of paradigm, it's really not only technically very, very powerful, but it's also conceptually very, very important and interesting. So it's not only ask what physics can do for you, but it also, you can ask what you can do for physics if you really understand this informational theory approach. And down here, I give this. I have a course which I normally teach at Weizmann, Skolkovo. I will teach this October at Skolkovo, and Harvard. I thought that I will teach probably at spring, hopefully if pandemic's over. But it's a very detailed lecture notes over here. This is a link where you can find all these things, and this is just a semester course, so there is a lot of things over there. Okay, so let me finish at this point, and now let me try to see how I would get out of it.